Today we're covering one of the most important yet least understood developments in artificial intelligence infrastructure. While headlines often focus on new AI models, chatbots, or video generators, the real arms race is happening beneath the surface, inside data centers. On February 10th, Cisco officially unveiled its newest high-performance switching silicon, the Silicon One G300. At first glance, it might look like just another networking chip, but Cisco says this chip is built for something much bigger, the gigawatt-scale AI era, and more importantly, the era of agentic AI. So what exactly is the G300? Why does 102.4 terabits per second matter? How can networking silicon improve AI job completion time by 28%? And why is networking suddenly as important as GPUs? Let's break it down. When most people think about AI infrastructure, they think about GPUs, NVIDIA H100s, Blackwell, TPUs, massive training clusters. But here's the problem. As AI models scale into trillions of parameters, it's no longer just about compute, it's about communication. Modern AI training doesn't happen on one GPU. It happens across thousands, sometimes tens of thousands, and those GPUs must constantly exchange gradients, parameters, updates, and activation data. If that communication is slow, your GPUs sit idle. Idle GPUs are the most expensive inefficiency in AI infrastructure, and that's where networking becomes critical. Cisco introduced the Silicon One G300, a next-generation switching chip designed specifically for AI data center fabrics. Let's talk numbers. The G300 delivers 102.4 terabits per second switching capacity, advanced shared packet buffering, intelligent load balancing, path-aware traffic engineering, support for ultra-dense 800G and beyond optical connectivity. But the headline figure, 102.4 Tbps, needs context. This level of throughput allows a single switch to interconnect massive GPU clusters without becoming the choke point. In AI training, even small congestion events ripple across thousands of GPUs, and that ripple effect compounds into massive time delays. Cisco claims the G300 architecture can reduce AI job completion times by up to 28% compared to non-optimized network fabrics. That is not incremental, that's transformative. Cisco repeatedly used the phrase, designed for gigawatt-scale AI clusters. This isn't marketing fluff. Hyperscale AI data centers are now consuming power in the gigawatt range. That's equivalent to a nuclear power plant or hundreds of thousands of homes. AI training is no longer a server rack problem, it's an energy infrastructure problem. As clusters scale into tens of thousands of GPUs, networking must scale proportionally. Otherwise, you build a supercomputer that cannot efficiently communicate with itself. The G300 is built to serve as the networking backbone in these ultra-large environments. Cisco also positioned the G300 as infrastructure for what it calls the agentic era. What does that mean? Agentic AI refers to systems that perform multi-step tasks, coordinate across tools, maintain memory, execute long workflows, act semi-autonomously. Unlike static inference queries, agentic AI produces bursty, unpredictable network patterns. You're not just sending a single prompt, you're orchestrating dozens of micro-interactions. This shifts network requirements from high bandwidth only to high bandwidth plus ultra-low latency plus adaptive routing. The G300 includes fully shared packet buffers, advanced congestion management, and path-based load balancing. These features ensure traffic doesn't stall when agent systems generate unpredictable spikes. Let's talk about the 28% improvement claim. GPU utilization is the percentage of time GPUs are actively computing rather than waiting. In large AI clusters, GPUs often wait for gradient synchronization, parameter updates, and collective communication operations. If the network slows down even slightly, GPUs pause, and when thousands pause together, training slows dramatically. By optimizing load balancing, buffer management, congestion avoidance, and fabric-wide coordination, Cisco claims G300 improves overall GPU efficiency.
Which leads to faster training completion, lower energy waste, better return on hardware investment. For hyperscalers spending billions on GPUs, a 28% gain is enormous. Now let's go deeper technically. The G300 uses Cisco's Silicon One architecture, designed for programmable high-scale switching. Key capabilities include fully shared packet buffering, allows dynamic allocation across flows, prevents buffer starvation, advanced telemetry, real-time network visibility, fine-grained congestion monitoring, path-aware load balancing, ensures traffic is evenly distributed, avoids microbursts and hotspots. High radix supports extremely dense port configurations. Liquid cooling compatibility, designed for AI data centers pushing thermal limits. AI networking must now integrate with liquid-cooled GPU racks. The G300 ecosystem supports these thermal requirements. Cisco is not alone. The AI networking battlefield includes NVIDIA with InfiniBand, Arista networks, Broadcom Tomahawk switches, hyperscaler custom silicon. NVIDIA's InfiniBand has dominated AI training clusters due to low latency and collective acceleration, but Ethernet is catching up fast. Cisco's bet is clear. Ethernet-based AI fabrics can rival InfiniBand performance at scale. The G300 is Cisco's flagship response to the AI infrastructure arms race. One of the most important ideas behind the G300 is something Cisco calls intelligent collective networking. AI training requires collective operations like all-reduce, broadcast, scatter-gather. These operations are sensitive to tail latency. If one GPU lags, the entire operation waits. Cisco's architecture focuses on minimizing tail latency through traffic shaping, flow isolation, congestion-aware scheduling. The goal isn't just speed, it's consistency, because in distributed training, consistency equals performance. AI clusters are power-hungry. Networking contributes significantly to overall power consumption. Cisco claims the G300 architecture improves energy efficiency per bit transferred. High-capacity switching reduces the number of required devices in the fabric. Fewer devices mean lower power, less cooling, smaller footprint. In gigawatt-scale deployments, even small efficiency gains translate into massive operational savings.
As AI transitions into persistent agents, autonomous systems, enterprise orchestration layers, networking becomes the circulatory system. GPUs are the brain. Networking is the nervous system. Without it, nothing scales. The G300 isn't flashy. It won't generate art, it won't chat, but it might be one of the most important AI hardware launches this year.
This launch signals something bigger. AI leadership is no longer just about models, it's about infrastructure sovereignty. Countries, hyperscalers, and enterprises are investing in domestic AI silicon, data center expansion, energy infrastructure, optical networking innovation. Cisco's G300 positions the company as a core enabler of AI at planetary scale. The Silicon One G300 marks a clear shift in AI infrastructure priorities, from raw compute expansion to optimized distributed coordination, from GPU scaling to fabric scaling, from training models to enabling autonomous agent ecosystems. AI's future will not be limited by ideas, it will be limited by bandwidth. And Cisco is betting that the next competitive frontier is not just intelligence, it's connectivity. That's it. If you like this breakdown, make sure to subscribe to the channel.